let us come to the first major topic of calculus, which is the topic on limits. Specifically, what we'll talk about in this for this topic is introduce to you the matter of what limits are, and see some of its applications, such as the matter of showing a function to be continuous at certain points, and then this matter of obtaining the tangent for a particular problem. Now, limits go a really long way. In fact, it's the fundamental building block of calculus. So it is our hope that you would have a very strong foundation right off the bat. Okay, so to come into the topic on limits, let us first consider the problem of tangents. Okay, so just to recall what tangents are, let's say we have a shape, right? Let's say a circle. The tangent to this circle at any one point, okay, suppose that point there, would be a line that touches the circle at exactly one point. If you have a circle and take any 2 points, right, connect them with a line, then what you will end up here is a line that crosses the circle at 2 points. And if the circle and in fact the line are all on a, let's say, XY coordinate graph, then what you can see is this line, right, you're able to obtain the equation of it, which is represented by y equals mx plus b, by noting where the y-intercept is for b, as well as the slope of this line, which can be obtained by the rise over the run between any 2 points on this line, which gives us this slope value m. Okay, so coming back to the matter of tangents, if let's say for a curve, we want to find the line equation for this particular tangent, which only crosses the function at that one particular point, is there a precise way of obtaining that instantaneous rate of change at exactly that location? The method that you're probably more familiar with in the past is obtain an average rate of change from one point to another and letting those 2 points to be close together. For instance, suppose we want the tangent at this particular point, then what you've learned is perhaps you could take this point here and that point itself and obtain the secant slope joining these two dots. Okay, then what you will end up with is some approximate value, and then you pick another point that's closer to it and obtain that secant slope, and then you obtain yet a better estimate of the instantaneous slope. However, you will not obtain the precise instantaneous slope, the tangent slope there. Okay, so in order to do so, we need the matter of limits. So let's go on to the next page here. Okay, so let's first of all define our secant slope. Okay, so let us just define this expression m of x to be the difference of our y values over the difference of our x values. And now let's say we are asked to find what is the instantaneous rate of change at a particular point at, let's say, x equals to a. So suppose we have a function that looks something like this, and let's suppose here is the point A, and we would like to find this tangent slope. Okay, alright, so borrowing the idea that we had in the past, we can pick any other point that's close to A, let's say this point here, and we obtain this the slope value, or yeah, the slope value, okay, right there for across those 2 points, right? So the slope, if this point is a generic point x, then the slope is just m of x. Okay, so this is what we mean by this function here. So with this function, right, what you could do is obtain a closer value to obtain x. Let x be some number that gets closer and closer to a. So as an example, if we were to find, let's say, the tangent slope for the function. Okay, so let's say the parabola y equals x squared, and let's say we want the tangent at 1, right? So now if we were to start off from x value being 2, which they would have these corresponding y values, then you can see the slope at the secant slope joining point 1 to 2, right? So since we want it at 1, so if we were to pick x to be 2, right, then what we would get is the rise over the run to be the value here in this case. 2 squared is 4, so 4 minus 1 over 2 minus 1, which is just equal to 3. Now the secant slope for, let's say, x value of 1.1. So now what we're doing is, suppose we pick a point that's closer now, say around there. Then the f value, or the y value for 1.1 is just 1.21. Okay, so let's write in everything here. So you can see the slope for that secant line now becomes 1.21 minus 1 over 1.1 minus 1, which gives us the value 2.1. Okay, so you can see here now the coordinate for y is getting closer and closer. Likewise with the x, the difference between the x, it's getting smaller and smaller. And now here we have a slope value of 2.1. Now if we were to pick yet a closer point, 1.01, let's say, then what we will obtain is the following, which is 2.01. So now you can see if we were to approach x equals 1 from the right along the x squared curve. Okay, so let's say if we were to approach down this path towards 1 from the right, then we can see the slope gets closer and closer to the value 2. Gets closer and closer to the value 2. Okay, now if we were to do the same thing from the left, of 1, let's say here's 1, and let's start off from the point 0. Then the secant slope using point 0 would be 0 squared is 0, so 0 minus 1 is negative 1. 0 minus 1, the denominator is also negative 1. This gives us a slope of 1. So this secant slope is 1. Now let's say we pick a point that's closer to 1 from the left. So let's say x being 0.9. So now 0.9 is up here. So now we're talking about this particular secant. So that particular secant would obtain the following for us. So what we have for the rise is 0.81 minus 1, and for the run is negative 0.1. So this evaluates to a secant slope of 1.9. And now let's say we pick yet a closer point to 1 from the left. Then what we will obtain here is 0.9801 minus 1 over 0.01 with a negative. So this evaluates to 1.99. So you can see that approaching 1, right, from the left and from the right, or approaching 1 from the left, we get a slope value that's getting closer and closer to the value 2. Okay, and approaching 1 from the right, we had 3, then 2.1, then 2.01. So we have a slope value that approaches 2 as well. So for that reason, we can say that the limit as x approaches to 1 for our secant slope calculations would be 2 for our case. Okay, which brings us to the topic of, well, what is a limit? and we will define this particular symbol on the next page. Okay, so what we will write is LIM, and then we can let X with an arrow pointing to A, and then we have our generic expression of X, so we'll just represent that with the letter F. Let me just write this again. And we say this limit would attain some number, which is maybe, we'll just use the capital L there. Okay, so what this means, in verbally speaking, it just means the limit of f of x, and as x approaches a, okay, equals the number L. Okay? So whatever you see here in this box, okay, verbally means that the limit of f of x approaches is equal to L as you have x approaching a. Okay, so another way of saying it is as x approach a, f of x approaches L. Okay, so these are identical from one another. Alright, so what this means, okay, is that your x gets closer and closer to a, but it does not attain the value a. Okay, so notice that x approaching a has a different symbol than saying x equals to a. When we say x equals to a, we actually mean that x has that value. And if x has the value, then when we talk about a function evaluated at a, then it would just be the evaluation of that expression, replacing all the x with a. However, that's not what we're talking about right here regarding to limits. For limit, x approaches a. So that means that our x is very, very, very close to the value a, but not at the actual number a. Okay, so earlier when we were talking about the limit as x approaches to 1 of f of x, or in our case it was m of x, so I'll just use m of x. Okay, limit as x approaches to 1 of our expression of x. Okay, this just means that our x gets closer and closer to 1. Okay, so that's represented by our quick exercise of writing x to be 2, then x to be 1.1, then x to be 1.01, and then we evaluate those values that are close to 1 from the right in this expression. Okay, and then we do the same thing, but from the left of 1, starting with 0, then 0.9, then 0.99, and then we evaluate those three with the same expression m of x. And numerically, you would see that this limit would evaluate to the value 2. Okay, so that's exactly what it means. Okay, limit as x approaches to a of f of x would equal to some number L. Okay, so all this means is that we only care about what's going on near a, but not exactly at a. So I hope this gives you an idea of what we're talking about regarding limits. So the very first video on limit, okay, what you should take home is the following in red. Okay, so in red, I'm just going to put a box around all of this, and this is the definition of our limits.